bootstrapping BPS spectra of 5D, 6D SQFTs. And this talk is based on the following two papers with my student Min-Sung Kim and Sung-Soo Kim at UESDC and Gi-Young Lee at KAIST. In the first paper, we discussed the improvement of blob approach for arbitrary 5D, 6D SQFTs. And in the second paper, we studied a new blob formalism for Wilson loop operators in this series. So we are basically interested in the Witten index, counting BPS spectrum in 5D or 6D SQFTs. It's defined in the following way. And the states captured in this index are labeled by their angular momentum J1 and J2, and also R symmetry JR, and the gauge charge phi and flavor charge H. And epsilon 1 and 2 are the chemical potentials for the angular rotations, and phi is the Coulomb branch parameter, and m is the flavor mass parameter. So when you define the Witten index, we usually use a Fermion number here, but here we instead use 2JR. This is mainly because we want to use the same definition of the Witten index, even in the presence of the magnetic flux on the blob background. Which maybe I'll talk about later. Okay, so this index is basically the same as Nekrasov's instant to partition function in 5D gauge series on omega background. And in 6D, this index computes the elliptic genera of self-dual strings on the tensor branch. And geometrically, it's interpreted as the topological string partition function or Go-Bachmann-Baffa invariant, which counts the holomorphic compact two cycles in local Calabi threefold. We usually compute this index by using localization on instant moduli space using ADHM construction, or by using topological vortex method in local Calabi threefold. However, such traditional approaches are quite limited only for very special cases. So today I'll introduce a systematic and a universal approach to computing this kind of WPS index with or without Wilson loops for any 5D, 6D SQFTs. So here I'd like to emphasize the word any, which include the 5D KK series as well as the 5D SQFTs. But for this method, I'll assume the following: a UV complete or UV finite 5D, 6D SQFTs has on their Coulomb branch or tensor branch either the gauge theory description in 5D or in 6D, or geometric description, or can be obtained by algebra laws of one of these descriptions. I think this is a reasonable assumption because all the known 5D, 6D QFTs have one of these descriptions. So this is my plan. I'll first start with a brief review on the 5D and 6D SQFTs and their compactifications. And then I'll explain the Nakajima-Yoshioka's flow formula and its generalization. And then I will discuss how to solve this flow formula to bootstrap the BPS spectrum of 5D, 6D QFTs. And then I'll introduce a new flow formalism for Wilson loop operators and then conclude this talk. Any question? So please interrupt me anytime whenever you have a question. So let me start with 5D and 6D SQFTs. So I think most of you are already very familiar with this stuff. So I will give you a very brief introduction to 5D gauge series. So in 5 dimensions, such gauge series preserve A-spot charges and SU2R symmetry. And the theory consists of the vector multiplet and hypermultiplet. And we are basically interested in the particle spectrum on the Coulomb branch of these theories. And the Coulomb branch is parameterized by the scalar field phi in the vector multiplet. And in 5D, for each gauge group vector, we have the topological current J defined in the following way. It's the Hatch dual of FHF. And this topological current play very important roles in various non-trivial physics as strong coupling. And 5D gauge series are not renormalizable, so they become free series at low energy. So maybe these series are trivial series. However, in '96, Cyborg proposed that actually the certain class of supersymmetric field series admit non-trivial UV CFT fixed point. And famous examples are SU2 gauge series with fundamental flavors. And actually, this series was discussed in serious talk on Monday. And recently, lots of progress has been made for this kind of non-trivial 5D gauge series. So on the Coulomb branch, we can integrate out all the charged methods. Then at low energy, the series will become abelian gauge series with interactions characterized by so-called prepotential. And prepotential takes the following expression. It's the cubic polynomial in the Coulomb branch parameter and also flavor mass parameter. And more importantly, it's one of exact. So for a given gauge series, we can exactly compute this prepotential. And these two terms are coming from the classical contributions. The first one is from the Baer-Kinect term, and second term is from the Chern-Simons term. And this term is the one contribution, which we can compute by evaluating this triangle diagram for the fermions, gauge-nos, and meta-fermions. Then on the Coulomb branch, the effective coupling is set by second derivative on this prepotential, and also metric on the Coulomb branch is determined by this effective coupling. The low energy theory also involves the various Chern-Simons couplings. So there are cubic Chern-Simons terms for the gauge and flavor symmetries, and the coefficient in front of this Chern-Simons term is computed by taking the third derivative on this prepotential. There are also linear mixed Chern-Simons terms, and the first term is the gauge and gravity mixed Chern-Simons term, and second term is the gauge asymmetry mixed Chern-Simons term. And also these coefficient can be evaluated by computing the fermion one-loop diagrams like this one and this one. But the point here is that for any given gauge series, we can evaluate all these topological terms exactly. Okay, and also as we will see later, these Chern-Simons terms are very crucial input to formulate the blow equation. Therefore, to bootstrap the BPS pattern, I will explain about them later. So let me explain the geometric counterpart of this field theory. 5D component field theories can be geometrically engineered in M theory, compactified on the local Calabi-Yau threefold. And the low energy physics in the field theory are basically determined by the geometric properties of this internal Calabi-Yau three. And this local Calabi-Yau threefold can be realized as a local neighborhood of a collection of Kähler surfaces like this. So here Si are the component surfaces. And we collect all these component surfaces together and we can form a bigger Kähler surface, and embedding them into the Calabi-Yau three, we can, and taking the decoupling limit in M theory, we can engineer 5D CFTs. And the number of this component surface is basically the dimension of the Coulomb branch in the field theory. And each component surface Si is either a local P2 or a Hertzog surface Fn, or they are blow-ups. And these are some examples. So this is P2, and this is F0, F1, and this is a blown up F0. And this component surface itself can also engineer rank 1 5D gauge series or 5D field series. For example, F0 realize the SU2 gauge series at theta equals 0, and F1 realize SU2 at theta equals pi, and so on. We can also glue these component surfaces together to form a bigger surface embedded in the Calabi-Yau threefold. So this is the example of gluing two surfaces. So in this example, we glue F0, one Hertzog surface F0, to another Hertzog surface F2. But here, to glue them together, we identify the curve here to the curve in F0 together. And at the end, we'll have the rank 2 surface And embedding this surface into Calavia 3, we will have the rank 2 Calavia 3 geometry. And in fact, this geometry realized S3 gauge theory at Chern-Simons level 1, and more complicated higher rank geometries. Therefore, higher rank field theories can be engineered in this way by gluing multiple component surfaces. So this is the dictionary between the gauge theory data and geometric data. The Coulomb branch correspond in the gauge theory or in the field theory correspond to the Keller cone of the internal Calavia 3 fold. And particles in the field theory are coming from M2 branch wrapping compact holomorphic 2 cycles, and monopole strings are M5 branch on the 4 cycles. And geometrically, the Chern-Simons terms in the field theories are interpreted as follows. So that we have triple intersection in the field theory, and it's nothing but the cubic Chern-Simons coefficient here is mapped to the triple intersection of 3 divisors in Calavia 3 fold. And the gauge gravity mixed Chern-Simons coefficient is the intersection of the Chern class of Calavia 3 with the component surface SI. However, this mixed gauge asymmetry mixed Chern-Simons coefficient has no geometric interpretation, but we can actually deduce this coefficient for the geometry from the field theory computation that for each surface, this coefficient is always 2. Okay. Again, point here is that for the given Calavia geometry, we can identify the corresponding field theory and also can easily compute all these Chern-Simons topological coefficient. There are also another interesting class of 5D field theories, so-called Collagen theories. They are in fact shift theories coming from compactifying 6D SQFTs on a circle. And when we do the compactification to 5 dimensions, we can perform the auto-automorphism twist. And there are 2 types of twist. One is the gauge twist acting on the gauge algebra. And second one is the tensor twist, which actually folds tensor nodes. Such kind of automorphism twist of this shift SQFTs when we do the compactification can realize more general 5D Collagen theories. And geometrically, such Collagen theories are engineered by M theory, compactified on elliptic Calavia 3 fold for untwisted ones, and or genus 1-fibered Calavia 3 fold for twisted ones. And effective prepotential and also Chern-Simons coefficient can be exactly computed for any given Collagen theories by taking into account the classical contribution and Grishvaric contributions, as well as one-loop contributions coming from the Collagen momentum stage. So this is the summary. This is called the effective prepotential evaluated on the omega background, but I will come back to this point later. But so here, I'll not explain the detailed structure of this low energy data, but point here is that for the given Collagen theories, we can evaluate their low energy prepotential and Chern-Simons terms exactly again. Okay, any questions so far? Okay, now I'll explain about the flow of formalism. So Pilchin, you have something to say? Okay. So we'll consider 5 SQFTs on blow background. So blow background is nothing but the C2. And now origin of C2 is replaced by a P1 or 2 sphere like this. So this is called blow background. And this blow geometry is basically the same as C2 geometry, except the origin, which is now replaced by P1. So why are you interested in this blow background? Nakajima and Yoshioka actually computed the partition function on this blow background for pure 5D and 4D SU and Super-Yang-Mills series. And they found that the partition function is in fact taking the following factorized expression. So this blow background has 2 fixed points under the Lorentz rotations. One is the south pole and north pole on this P1. So after taking the localization computation, it turns out that the partition function on this flow background is factorized into two partition functions. One is coming from the south pole and the other one is coming from the north pole. And also we can turn on the gauge magnetic fluxes on this P1. So as a result, the final form of the partition function is given by the sum over all the gauge magnetic fluxes. Here, M vector is the flux vector for the gauge symmetry. So it's given by sum of all these gauge magnetic fluxes, and each flux vector or sector is given by the product of these two partition functions. So these two partition functions are actually partition function localized near each fixed point. And it turns out that the geometry near each fixed point is also the same as the ordinary shift background. Therefore, this localized partition function also takes the form of the ordinary shift partition function. But in the presence of the magnetic flux, the parameters are shifted. Okay? So this is the Brunner partition function. Now we'll think about the smooth transition from this flow background to the ordinary C2 background without the P2 at the origin. Okay. It turns out that this flow partition function is independent of the volume of the P1. Okay, so this is the smooth transition, shrinking the P1 cycle. Because this flow partition function is independent of the volume of P1, after the transition, we will get the same partition function. But since we are now going back to the original C2, we can expect that the partition function should reduce to the ordinary C2 partition function. Okay, this will lead to the following interesting relation.
Excuse me, can I ask a short? Yeah, I mean, I understand that. Yeah, I understand that the blow-up volume does not appear in the partition function, but still, can we guarantee the absence of any discrete difference? Blowing up and not blowing up is discretely different. It might be, right?
Yes, but at the level of partition function, we don't have the parameter dependence. So I don't
yes, but that's why I'm saying it can be discretely different. It might be, who knows?
Yes.
I mean, for concrete example, you can compute and compare, but can you give a general statement for any omega different partition functions on C2? Actually,
this blowification hasn't never been derived from the first principle like localization. So I cannot guarantee if there is any discrete difference between these two partition functions. But here in this talk, I will just trust this relation and show that the partition function can be computed by solving this equation. But it's a good point. Yeah.
Thank you. Thank you.
Yeah. Any other question?
So maybe adding to adding just a bit. So it is actually known that there's some scheme dependence in this blow up type formula. So that for certain gauge theories, like the instantons on say orbifold, like local ALE space, then there's some known scheme dependence which result in two different results. So, but in some sense, that gives you a relation that changes this lambda factor. But
sure.
Yeah.
So can you repeat the last sentence?
Yeah. So for example, if you consider like the SU2 gauge theory with 4 fundamentals and compute the instant partition function C2 mod say Zn or something, then you can compute the partition function in two different ways. One is using the blow-up type of equation, and the other is using the orbifold type constructions. And it's known that they actually give you two different answers up to a factor. And that is understood as some kind of wall crossing phenomena in the Donaldson invariant, where there's a wall at the Fi parameter being 0 and non-zero. So yeah, so there's no guarantee that such thing cannot happen in general. But even if that happens, the difference seems to be minor. So that's fine.
Okay, thank you for the comment. But yeah, as I said, I don't have the concrete proof that there is no such discrete difference. But in this talk, I just trust this relation.
Yeah.
Thank you. So here lambda is a constant, okay? And interestingly, on the left-hand side, we have the magnetic flux dependence, but on the right side, we don't have magnetic flux. So it tells us that for a given theory, we can have different choices of magnetic fluxes. So we can have multiple blowifications, which should be satisfied by the same C2 partition functions. So it turns out that this blowification can be solved. You can expand both sides in terms of the electric charges or Universality, and you can solve order by order in the expansion and bootstrap the BPS spectrum. This relation recently have been studied extensively, and this was first found by Nakajima Yoshioka for the 4D and 5D SUN super Yang-Mills theories. And 5D super Yang-Mills theories with the exceptional gauge groups and methods has been studied by these two papers. And the blowifications for the topological strings, partition functions for the local threefold was proposed in this paper. And its elliptic generalizations for the strict SQFTs has been proposed in this series of papers. Today, I further improve this blow approach such that it can be applied to arbitrary 5 and 6D quantum field theories. So we can basically summarize the blowification in the following way. It accepts two inputs. First input is the effective prepotential. I will explain shortly. And second input is the magnetic flux on the P1. And once you prepare these two inputs, you can put them into the blowification. Then blowification will spit out the BPS spectrum. So it's kind of the generator for bootstrapping the BPS spectrum of the 5D field theories. But we need to know these two inputs for a given theory. Okay, let me first explain the first input, which is the effective prepotential. So blowification is the equation for this partition function of omega background. And actually this partition function is factorized in the following way. The first term is a kind of prefactor, which is the collection of the regularization factors when you compute the partition function. And the second term is GGV, which is the Gufa-Vafa invariant, which captures all the index part of the partition function. Here, M is the vector for the Keller parameters, and D is the charge. So Gufa-Vafa invariant count the degeneracy of the state for the given charge B. And this prefactor is the regularization factor. And interestingly, it turns out that this factor is nothing but the effective prepotential at low energy on the Coulomb branch evaluated on the omega background. And it can be written as the collection of the Chern-Simons terms at low energy and their supersymmetric completions. But now we will evaluate all this low energy action on the omega background. Then this is the result. As you see, F is the prepotential on the Coulomb branch, and CG is the gauge gravity mixed Chern-Simons coefficient, and this CR is the gauge asymmetry mixed Chern-Simons coefficient. And as I explained, all these coefficients can be exactly evaluated for any 5D field series and also KK series. Therefore, first input can be easily prepared for arbitrary 5D and 6D QFTs. And second input is the quantized magnetic flux. As I explained, we can turn on flux on this P1 for the gauge symmetry and the flavor symmetry, but they should satisfy proper quantization condition. Otherwise, the formalism or blowification breakdown, and there would be no solution to them. And magnetic flux F should be quantized in the following way. For the state of the spin JL and JR, or for curve in geometry with this spin, the flux should be integrally quantized if the 2 times the spin sum is odd, or half integral otherwise. Okay, so in the field theory, it simply means that W bosons should fill the integral flux. On the other hand, the hypermultiplet should fill half integral flux. You can simply say that all the BPS scalar field or bosonic BPS state should fill integral flux in the field theory. And we can actually, there are several choices of such quantized magnetic fluxes, in fact. And it turns out that the number of such choice for the magnetic fluxes satisfying this quantization condition is like the law of vacation to bootstrap spectrum. Let me give you some example. And in 5 dimensions, there are 2 types of SU2 gauge series. One is the SU2 at theta equals 0, and another one is the theta equals pi theory. They both have geometric realization. Theta equals 0 theory is realized by Hertzsprung space F0. On the other hand, the theta equals pi is realized by F1. And these 2 theories perturbatively have exactly the same spectrum. They have W bosons with the mass 2 phi. Okay, so we cannot distinguish these 2 theories perturbatively. On the other hand, they have different instanton spectrum. Okay, instanton, the ground state of the one instanton is the state is coming from this curve in F0 with mass 2 pi plus m. And it turns out that this state coming from this cycle is a vector multiplet. On the other hand, the instanton state for this F1 or SU2 at theta equals pi theory is a hypermultiplet. So these 2 theories are distinguished by the instanton spectrum. We can compute the effective potential on the omega deformation background by using gauge description or kind of geometric descriptions, and this is the result. Since they have the same, they have the same. So the formulation for these 2 theories are the same. However, they are distinguished by differently quantized magnetic fluxes. As I said, F0 has instantonic state, which is a vector multiplet. On the other hand, F1 has a hypermultiplet instantonic state. So therefore, the flavor symmetry, this flavor symmetry is basically U1 topological current for the instantonic state. For this flavor symmetry, the magnetic flux for the theta equals 0 theory should be integrally quantized. On the other hand, theta equals pi theory have half integral magnetic flux. Okay, so second input can be also prepared, and by putting this first input and second input together into the law equations, you can compute the BPS spectrum of these 2 theories. And it turns out that the result from the law equations perfectly agree with the ADHM result for these 2 theories. So I think our blob approach is kind of universal because, as I explained, the 2 inputs can be easily prepared for arbitrary 5-density QFTs. So in our paper, to show such a universality, we computed the BPS spectra for all rank 1 and rank 2 Collagen theories by solving the blob equations. So these are the results for all rank 1 and rank 2 Collagen theories. And it also means the spectrum of all rank 1 and rank 2 5D CFTs can also be evaluated by solving the blob equations, because all such 5D CFTs can be obtained by algebras of from one of these KK theories. Among them, these 4 theories have no other method to compute their spectrum. So our blob approach provides a way to compute the partition functions for these 4 theories. And also in our paper, we computed the BPS spectra for new 5D CFTs having no gauge theory description and also no geometric realizations. But they have the brane realizations, which is found in our paper. So even for the theories having no gauge and no geometric realizations, our blob approach can be applied and we can bootstrap it to compute their spectrum. So this blob approach is quite powerful tool. Let me give you one interesting example. This is the SU3 gauge theory at Chern-Simons level 8. This theory is interesting because in our paper, actually, we conjectured that this theory doesn't have UV completion. It's basically from the fact that the geometric realization of this theory is not shrinkable. So let me explain it. So this geometry is realized by gluing F0, two Hertzberg surfaces, F0 and F1 in the following way. And it turns out that this geometry has three primitive curves. And these three primitive curves cannot have positive volumes at the same time in the UV limit. UV limit is basically the limit we turn off this mass parameter. It simply means in this geometric page, we cannot find the CFT fixed point. Okay, so it's not shrink-able, and because of this fact, we first conjectured this theory will not have UV completion. However, it was too fast. Actually, in this paper by Bud Watts, he conjectured that this theory can have the UV completion. His argument based on the following duality between G2 gauge theory with one of the joint hypermultiplet and SU3 gauge theory at level 15.5 plus one fundamental hypermultiplet. Okay, so if this duality holds, then this SU3 gauge theory at level 8 can actually obtained by an RG flow from this SU3 gauge theory by integrating out the fundamental hypermultiplet. So it means this SU3 gauge theory will have a UV completion. So now it's puzzling because geometrically it's not shrinkable, therefore it cannot have UV completion. But on the other hand, there is a prediction for the UV completion for this theory. So we have to resolve this puzzle. Actually, we can resolve this puzzle by looking at the fact that this one of these primitive curve, basically it provides the instantonic state, is an exceptional curve, realizing a hypermultiplet. Because it's an exceptional curve, we can flop it and move it onto another chamber, and probably in the another chamber we can find the CFT fixed point limit. Okay, so maybe the chamber after the flop transition would be a unitary chamber such that we can attain the CFT fixed point in the chamber. We can check if it's true by looking at the spectrum of the theory. We computed the spectrum of this theory by using the blow vacation, and this is the result. And it turns out that all the states captured by this table and captured by blow vacation have non-negative masses in the UV limit, except these three states. Okay. And it turns out that these three states are coming from exceptional curves. They are hypermultiplets. Okay, so we can plot all these three hypermultiplets. Then all the spectrum in the theory, in the chamber after the flop transition, will have non-negative masses in the UV limit. Therefore, the chamber after this series of three flop transitions will realize a chamber which we can see the UV fixed point at the origin. Okay, so our computation provides a very concrete evidence for the existence of this SU3 gauge theory at Chern-Simons level 8. Okay, let's move on to the blow vacation for the Wilson loops. So in 5D gauge theory, half of BPS Wilson loop operators are defined in the following manner. It's a loop operator, a gauge invariant loop operator, and it's labeled by its representation under the gauge symmetry. And we are interested in the particle spectrum bound to the Wilson loop operators on omega background. And this spectrum is captured by this Wilson loop partition function. Here, trace is taken over the state in the presence of the Wilson loops. And we can also consider the expectation of this Wilson loop operator as a normalized partition function. We normalize this Wilson loop partition function by the Baire partition function. And actually, this normalization removes all the bulk states which do not form any bounded state to the Wilson loop operator. So we can say that this expectation value counts genuine 1D spectrum. Therefore, this expectation value can be written as the sum of 1D particle spectrum like this. We can also give another interpretation for this Wilson loop expectation value. It will count the BPS bounded state to a very heavy actually infinitely heavy 1D defect with electric charge. And this electric charge corresponds to the Lewis weight of the representation R. For example, the fundamental Wilson loop in SU2 gauge theory at zeta equals 0, the each expectation value can be computed by using the ADHN construction, and this is the result. Then expectation value can be divided into this classical contribution, and all other terms are the instanton contributions. Okay, and classical terms, as we expected, we have two classical terms, and instanton corrections can be computed by using the ADHN construction. And we can further expand this Wilson expectation value in terms of the Coulomb branch parameter, and we have this expression. As you see, you can interpret each term in this Wilson expectation value as the terms coming from the bounded state to this lowest weight state, corresponding to this 1D heavy defect. Okay, so this first term is the lowest weight state, and second term is the bounded state of the bulk W boson with charge +2 with this lowest weight state. And third term is the instantonic bounded state to the lowest weight state, and so on. Okay. So this definition can be used to define the Wilson loop operators in geometric fashion. So in geometry, the Wilson loop operator is interpreted as an operator creating an empty brane state wrapping a primitive non-compact two cycle. Here, primitive two cycle, non-compact two cycle simply means it's a non-compact two cycle intersecting non-negatively with all compact four cycles. So it will satisfy this condition. Actually, the same definition, similar definition of the loop operator was discussed by Sacrasto on Monday. So this primitive cycle actually determines the representation of this loop operator. We can define the representation as the electric charge for this primitive two cycle, which is given by the intersection with the compact four cycles. And the expectation value of this loop operator in geometry counts holomorphic two cycles bound to this primitive non-compact two cycle. So let me give you an example. For example, the fundamental Wilson loop in Hertzberg surface F0, which corresponded to SU2 gauge theory at zeta equals 0, can be considered as the M2 brane state wrapping this non-compact two cycle and its bounded state or other non-compact two cycles, which is given by a linear sum of this primitive curve and other holomorphic compact two cycles like this. So the lowest weight state is simply this red line wrapping this curve C, and the state, the second state in this expression in the field theory corresponded to the bounded state of C plus the, the fiber class in geometry. And the instantonic state comes from the another non-compact two cycle, which is a linear combination of this primitive curve and the base curve H, and so on. So this is a geometric interpretation of the state we count in the Wilson expectation values. So let's now consider the blow equations for the Wilson loops. In the blow background, we have two fixed points, and we can actually put two independent Wilson loops at each fixed point, okay? And we will consider blow down procedure to the usual C2. Then you can easily imagine that these two Wilson loops will merge into a single Wilson loop after blow down. And this Wilson loop will now take a product representation, R1 times R2, okay? And this transition actually led to the following interesting equation for the Wilson loops, okay? So now we have two Wilson loop expectation values. One is from North Pole and second one is South Pole. And they will be identified with the Wilson loop operator on the usual ordinary C2 background at the origin. Okay, so this is our proposal for the Wilson loop blow equation for the Wilson loop operators. So diagrammatically, this flow vacation for the Wilson loop operators can be interpreted in the following, as the following black box. It will now accept 3 inputs. First 2 are the same as the input to the ordinary flow vacation, but now we have one more input, which is nothing but the representation of the Wilson loop. So here we can put 2 Wilson loop operators, but we can set, for example, the second Wilson loop is trivial. Then we will get a relation which connect the Wilson loop, the same Wilson loop living in the C2 background, and also the same Wilson loop in the flow background. Therefore, using this input, these 2 input together with the representation, we can compute the Wilson loop expectation value by putting them into the flow vacation. So this is the summary of the flow vacation for the Wilson loop operators. By the way, if you put all the trivial Wilson loops here and here, then this flow vacation reduced to the ordinary flow vacation without loop operators. Okay, let me give you some example. So we can even define the Wilson loops in non-Lagrangian series and their spectrum using the flow formula. This is the example for the local P2 series. Then the fundamental Wilson loop in this geometry is defined as the loop operator with the minimal charge. It comes from the non-compact primitive 2-cycle C intersecting P2 at one point. Okay. Once you insert such operator or such non-compact 2-cycle or M2 branch wrapping this 2-cycle, the theory will also have a bound state coming from the C plus L. L is the line in P2 and so on. Okay. We can compute the such non-compact 2 cycles, which is given by a linear combination of the primitive curve, non-compact curve C, and also holomorphic curves, compact curves in the geometry. Then the flow vacation tells us that expectation value of this minimal Wilson loop in P2 is given by this expression. Okay. So the first term is coming from the primitive curve C, and second term is the bound state C plus L, and third term comes from another bound state C plus 2L and so on. And we can actually compute all the higher order corrections by evaluating or by solving the flow vacations. Therefore, our flow formalism for the Wilson loop provide even a method to compute the expectation value of the Wilson loops in non-Lagrangian series. Okay, under the duality, these Wilson loops are mapped quite non-trivially. Okay, so let me give you one example. We'll consider SU3 gauge theory, and this theory enjoys very interesting duality. This theory has a dual G2 gauge theory, and these two theories are realized in this single geometry. So the geometrically, this SU3 level 7 gauge theory is realized by gluing 2 Hertzberg surfaces, F0 and F8. And actually, the duality exchanging SU3 and G2 gauge group is nothing but the duality in F0 theory exchanging the base and fiber class. And we can also put the Wilson loops in these 2 dual gauge theories, and duality will map one Wilson loop in one gauge theory to another Wilson loop in the dual gauge theory. Under this duality, the Wilson loops in SU3 gauge theory is quite non-trivially mapped to the another Wilson loops in G2 gauge theory. For example, W0-1 is the fundamental Wilson loop, which is now mapped to the adjoint Wilson loop in G2 gauge theory. On the other hand, the anti-fundamental Wilson loop is mapped to the fundamental Wilson loop in the G2 gauge theory. Actually, classically, these 2 Wilson loops are related by the complex conjugation relation, but actually the charge conjugation for this SU3 gauge theory at level 7 is classically broken by the Chern-Simon terms with the level 7. So we didn't expect that they are complex conjugate anymore in the instant corrections. And we can check under the duality. In fact, these 2 Wilson loops are mapped to the completely independent Wilson loops in the dual G2 gauge theory. We can check if this duality works well by looking at their spectrum. There are no other methods to compute the Wilson loop expectation values in SE3 level 7 gauge theory and also G2 gauge theory, but we can evaluate these expectation values by using the Blow formula. These are the results. The first one is the fundamental Wilson loop expectation value, and second one is anti-fundamental Wilson expectation value. And the first three terms are the classical contributions, and the state in this box are the instanton corrections we computed using Blow equations. So we can compute their expectation values. And also we computed the dual Wilson loops in G2 gauge theory and checked that they completely match. So this duality map between Wilson loop expectation values can be checked by computing their spectrum. Therefore, our Blow approach for the Wilson loops provide another concrete tool to check the dualities. Okay, let me conclude. So as I said, the partition function of 65D QFTs and Blow background provide Blow equation for BPS spectrum. And we provide a significant generalization for this method in terms of effective prepotential and quantized magnetic fluxes. And we also introduced a new Blow formalism for Wilson loop expectation values in this series. And as I said, we haven't derived the Blow equation from the first principle. So it's worth doing such computation to show there is no ambiguity like the discrete ambiguity so pointed out. But I haven't tried, but maybe someone should do it. And also, I said that maybe our approach can be used for all 5D and 6D SQFTs. And I also explained how to apply this formalism for arbitrary 5D and 6D QFTs, but it doesn't guarantee the solvability of the Blow equations. So proving the solvability would be another interesting future project. And I provide the Blow equation for the bare partition function and also Wilson loop expectation values. However, there are lots of interesting other partition functions with other types of defect and also on other background. So maybe finding new Blow equations for such other observables would be another interesting future task. Okay, let me stop here. Thank you.
Thank you. Questions, comments? Raise your hand or speak out.
Can I ask one question?
Yes, Asaf. Yes, please.
Can you change the logic and demand the solvability of Blow equations to discover new QFTs?
Very good question. So actually, I was trying to do that even for rank 1 theory.
Yeah.
But so far, it was not very successful. But I expected maybe we can use this Blow formalism to classify or find the new 5D CFTs. Yeah, it's very good question.
Okay, thank you. Thank you.
Anyone else? Cyril?
Yes. What
Yeah.
you know? Is there does anything change if you look at the different global structure of the, for instance, SU2 or SU2 level 0 or SO3? You would sum over more magnetic flux or something like that?
I think this Blow equation without defect, I mean first, just count the local excitations, the local particles. So the global structure or the one-form symmetry action, the 1D defect like Wilson loops. So I think this Bell partition function will not depend on the global structure. However, Wilson loop expectation values depend on the global structure. If you change the global structure from SU2 to SO3, then you have to sum over the background magnetic flux for the one-form symmetry acting on the Wilson loops. Then it will kill the fundamental Wilson loop expectation value. So it will affect the Blow equation for the Wilson loops, I think.
But so even for the standard one, I mean, because you do have a sum over the magnetic fluxes or whatever gauge group you're considering. So, but
Yeah.
Result
I think the global. Yeah. So actually, the magnetic flux for the gauge symmetry, the choice of magnetic fluxes for the gauge symmetry depends on the center, the element in the center symmetry for the gauge group. But for any choice of such a center symmetry, I got the same partition function, actually. So I think the global structure doesn't affect this kind of BPS, bare BPS spectrum.
Right.
But yeah, I didn't check for all the series. So
right. So the equations are different. So it's a direct. If you wanted to check, then that
right.
It only counts.
Yeah, equations are different.
Yeah,
exactly. As I explained, the equations are different for the choice of the magnetic fluxes, but results are the same.
Yeah.
Quite interesting.
Okay. Anyone else?
Can I ask one more question?
Sure.
Yeah. Can you apply the blow-up techniques beyond quantum field theory? Something like little strings or 5 or 6 dimensional quantum gravity?
Yeah, very good question again. For little string, I expect that it will hold, but I've never tried. And actually, I tried to see if we can find the blow equation for the compact Clavier realizing the 5D or 6D quantum gravities. But crucial fact is that blow equation requires the refinement. So if you look at the formalism, then this shift due to the magnetic flux depends on the 2 epsilon parameters, which requires the refinement of the blow equation. But in quantum gravity, since we don't have SU2R symmetry, which we can use for this refinement, therefore, since we don't have a refined partition function defined on the quantum gravity theory, it was very hard. Actually, I failed to get some consistent blow equation for it. So I'm not sure, but it's not easy.
Is it also true in 5 dimension, lack of one symmetry?
Right. It's the same.
Okay.
Yeah.
Thank you.
But yeah, it's a good question. We should try. But yeah, so far I've always failed.
Thank you.
Yeah. Does Jaewon has question? No? Just show yourself. Anyone else?
Can I ask a question related
Yes,
to the
Futoshi.
current one? Yes, thank you. So you said that you need to compute a refined one, but is it still useful for computing unrefined partial function? If we compromise knowing unrefined one is enough, then is this blow-up formula still useful or becomes completely useless?
So you are assuming that we have only unrefined partition function.
Yes.
And we want to check if undefined partition function satisfies.
Sorry, maybe the opposite. If the purpose is to know unrefined partial function is enough, then sorry. What's the problem? Sorry, maybe what I'm saying sounds nonsense.
I mean, we will keep this session open for, next 2 hours or so. So if people want to stay and converse, you are very welcome to do this in much more detail.
Okay, thank you.
Yeah.